And then he moved back to Europe, and he did a PhD in the University of Paris-Orsay, that is Saclay right now, right? Is the,
yes.
Yes, okay. And finally, is it okay? Ayrton is going to present. I didn't know.
No problem. You can continue. No problem.
Okay. And therefore, I finish the introduction and then I give, okay, yeah. So we will have 2 introductions today, even better than usual. So finally, as I said, he moved to Brazil. He worked for a while in Brasilia. And then he moved to CBPF, where he served several years as the head of the theoretical physics department. He's a physicist that is working in the area of statistical mechanics in the very broad sense, at the level that he worked in several topics, including more standard, like critical phenomena, chaos, nonlinear dynamics, but also topics that are a bit more exotic, like cognitive psychology, immunology, population evolution, and others. Since a long time, he's focusing on the concept of entropy and the foundations on statistical mechanics, and indeed, he is well known for having proposed in 1998 a generalization of the Boltzmann-Gibbs entropy in statistical physics. Now I pass the word to Ayrton, that is going to say something more.
Thank you. Your introduction is far more complete than mine. I will just add a few things. Well, it's an honor to introduce Professor Tsallis. He's one of the most prominent figures in contemporary physics, and he's well known for introducing the non-additive entropy, which leads to non-extensive thermodynamics. And why we are scientists is very happy when we are cited in the list of reference of some papers. Professor Tsallis is cited already in the title of the papers, where his name appears with terms like Tsallis distribution, Tsallis entropy, Tsallis statistics, and so on. So as Dario showed, this is a topic that goes far beyond physics, the border of physics. So he's known in different communities. And I would like to add one piece of information that is very recent. Professor Tsallis was invited to co-organize the Nobel Symposium of 2027. This Nobel Symposium is organized once a year in each of the areas of the Nobel Prize. So in 2027, the Nobel Symposium will be dedicated to study the generalization of Boltzmann statistics. And the symposium is titled Beyond the Boltzmann, Complexity, Memory, and Non-Additive Entropies. So it's an honor to have Professor Tsallis, and he is going to talk here about the world beyond Boltzmann-Gibbs legacy. Thank you.
Okay. Well, thank you very much for the introduction and for the invitation to come here. So, as I write here, we're going to go beyond the Boltzmann-Gibbs entropy and Boltzmann-Gibbs statistical mechanics, which are recovered as a particular case. So let me show to you this. I like to show this slide because Enrico Fermi, already in '36, in his book in thermodynamics, he wrote an interesting statement. The entropy of a system composed of several parts is very often equal to the sum of the entropies of all the parts. An intelligent man like Enrico Fermi wouldn't have written very often if he thought it was always. He wrote very often because he thinks it is not always. And then he says these conditions are not quite obvious and that in some cases they may not be fulfilled. And when this happens, this can play a considerable role. I'm going to talk to you a little bit about precisely the case in which the entropy is not the sum of the entropies of the parts. There is a word here that is missing. Enrico Fermi should have written several parts equal to, of several independent parts. He should have written this, but he didn't. But a young collaborator of him, Ettore Majorana, did. Ettore Majorana writes roughly the same thing, but he does introduce the word independent parts. And you will see this is an important issue. Okay, let me start with this little table. Here you have Boltzmann-Gibbs, Shannon, von Neumann entropy. And you have here the simplest expression, minus sum of p log p. And when all the probabilities are equal, this becomes this, which is on the grave of Ludwig Boltzmann in the Central Cemetery in Vienna. But I'm going to talk to you about this line, where you immediately see there is an extra index, q. If here you take q going to 1, you recover this line. So I'm not talking about an alternative where the magnificent Boltzmann-Gibbs concepts work well. I'm talking about a generalization, not an alternative. And this is based on this entropy, which, as you will see, will play an important role in the applications that I'm going to show to you, which concern basically complex systems in physics or elsewhere. This expression is one among 1 million possible generalizations of p log p. It's so easy to generalize a function. But why this particular generalization? That's a long story that I'm not going to describe here today. But let me tell you that these two have a lot of common properties, important properties, like concavity, extensivity, etc., but they must differ in something. Because if you want to generalize something here, you have to violate one of the properties of this something. If you violate none, you don't generalize, because the answer is that one. So we're going to violate something. What is it that we're going to violate? Additivity. This functional is additive, and this functional is non-additive. And you will, in a few minutes, see the difference. So let me okay. Let me rewrite the table that I just showed to you. So we introduce the function q logarithm of x like this, and when q goes to 1, this becomes the normal logarithm. This is the inverse function of this, and we call it q exponential of x. And when q goes to 1, this becomes the normal exponential function. I'm going to refer a lot of times to these functions, and using them, the same table that I just showed to you can be written in a more compact, more elegant way, which you see here, log, log, q log, q log. And the mathematician said that well represented, half solved. So it's good to have a nice representation of your problem, because, as we say in Brazil, é uma mão na roda. Now let's go about these two important words, additivity and extensivity. So additivity, I take it from the book of Oliver Penrose, Foundations of Statistical Mechanics, 1970. And then he defines that an entropic functional is additive if, for any two probabilistically independent systems, the entropy of the sum equals the sums of the entropies. It happens that SQ satisfies this, and therefore it is non-additive, excepting Q equal 1, where it comes back to the Boltzmann-Gibbs expression. So it is non-additive. So if you invent an entropic functional, in half an hour, you will know if it is additive or not. But I have another word here, extensivity. An entropy of a specific system or a specific class of systems with its ingredients, with its correlations and all kinds of complexities, that entropy is said extensive if it is proportional to n, for large n. So the word extensive is used in the sense of thermodynamics. Now, if you have the entropy that you invented, and you will find out that it is non-additive, you apply it to a system, and you want to know if that one is extensive. You will not know in half an hour. Maybe you will need 15 years to find out that, because you have to take into account the correlations between large n number of ingredients, and that typically is a big mess. So don't confuse additivity of the entropic functional, and when we apply this entropic functional to a particular system, we get an entropy of that system.
But at least, can we say that if it is additive, for sure will be extensive?
No.
No.
Because if it is additive and simple system, it will be extensive. But I will show in next slide, I think, counterexamples. So the answer is no. Here we have the counterexamples. So this is a specific class of systems. The total number of possibilities assumed to be equally probable increases exponentially with n. Like n coins, you would have 2 to the power n. If you have this, you should use Boltzmann entropy, because the logarithm of this is proportional to n, and it is extensive. And that is fine, because it satisfies the Legendre structure of thermodynamics. But, and this is the answer to the question, suppose you have a complex system in which the number of states does not increase exponentially with n, but n to the square, or n power 1.8. Then you don't want to use Boltzmann, because the logarithm of this is proportional to the logarithm of n. And you don't want logarithm of n. You want n, because this is obligatory to satisfy the Legendre structure of thermodynamics. So it doesn't work. SQ, in general, does not work either, excepting a magic value of Q, which is 1 minus 1 divided by rho, the same rho that you have here, that one is extensive. That's okay. This is what we want. So we have a non-additive entropic functional, but for a magic value of the index, it becomes thermodynamically extensive. And then we have thermodynamics in our pocket, which is very good to have. But suppose that it is neither this nor this, it is something like this. Then SQ doesn't work for any value of Q, no magic value of Q for this family. Then you have to invent another entropy. And there is such an entropy, S delta, and for delta equal 1 divided by gamma, the same gamma that you have here, that one is extensive, and that's okay. So, summarizing. I have here the Boltzmann-Gibbs entropic functional, which is additive. SQ, which is non-additive, S delta, which is non-additive, and so on. If the system that we are analyzing is of this type, W, assuming the simple case of equiprobability, if it is like this, then you should use Boltzmann, because this entropic functional, which is additive, is extensive for this family. And you should not use, in principle, SQ, neither S delta, neither other things. But if you have this family, you don't want to use Boltzmann entropic functional because it is non-extensive. And this is okay, and this is wrong, and this is wrong. If you have this family, you want to use S delta for this value of delta, and so on. So, if you married Boltzmann, you will stay here until the death separates you. I should tell you that there were thousands of physicists that would die here. But now there are only maybe hundreds, because most physicists have realized that this marriage is not good. There is a better marriage, which is this. And then, if you stay here, you are going to satisfy thermodynamics until the death separates you. So I'm going to work along this line. So my talk refers to this line, in particular, these kind of things. Not that one, because that one is in any book of textbook of statistical mechanics. So many of you have surely done graduate studies and with obligation to have good notes in Boltzmann-Gibbs statistical mechanics, which they call in the textbooks, because science is very slow, they call it statistical mechanics. I call it Boltzmann-Gibbs statistical mechanics. Because at the beginning of the 20th century, the people didn't say Newtonian mechanics. They said mechanics, because there was only Newtonian. But then became relativity, and then they started using relativistic mechanics, and then became quantum mechanics. So now the courses are not called course of mechanics. Now they are called course of Newtonian mechanics, because there are others, relativity, quantum mechanics, etc. Okay, so what I showed to you is kind of the central piece of this theory, but this central piece comes with many interesting properties around. And one of them is the central limit theorem. So the central limit theorem is called central because it is the most important theorem in theory of probabilities. Gaussians become Q-Gaussians within the theory that I'm talking you about, and with two mathematicians and Mario Gelman, we published generalizations of the central limit theorem that very briefly are here. If Q equal 1, this is to say if the systems are independent or quasi-independent, if the variance is finite, the attractor is a Gaussian. And this is why there are so many Gaussians in nature. If the variance diverges, and some mathematical delicatessen, the attractor is not a Gaussian, it is a Levy distribution, which is asymptotically a power law. These two are in any good book of theory of probabilities. But I'm talking about these two, when Q is different from 1, when the system has important correlations. In that case, if some variance is finite, the attractors are Q-Gaussians and not Gaussians. And here, if that generalized variance diverges, the attractors are what we call the Q-alpha stable distributions, which are these. I'm going to refer a lot to this because these appear all the time in nature, like these appear all the time in nature. In nature and elsewhere, as you will see. So let me start with a recent applications. There are, I don't know what to tell you, dozens and dozens and dozens of applications. So I had what in French we say l'embarras du choix, what to choose to show to you. So I choose half a dozen of interesting applications, and this is the first one, slow chemical reaction. So a couple of years ago, Nature published a paper by a group of Austria, Innsbruck, where they do a lot of ski. And in that paper, they analyzed this little reaction here, deuterium, hydrogen, this little thing. And it turned out that this chemical reaction is very peculiar, so peculiar that Nature chose their paper to make a highlight in Nature. And what is that paper? It is this, tunneling measured in a very slow ion molecule reaction. The group is this. The leader of the group is Roland Wester. And in that paper, they have this figure. In log linear, they have the distribution of velocities of the hydrogen molecules that are in the chemical reaction. And it is not Maxwellian. It is not the distribution that is in the textbooks. This is a Maxwellian, but it doesn't work. The system does not like Maxwellians. If the concentration of hydrogen is this value, it likes this, Q-Gaussian, with Q equal 1.15. If it is another value of the concentration, it likes this value, another Q-Gaussian. The system does not like Gaussians. It likes Q-Gaussians.
The standard Maxwell-Boltzmann distribution is also not a Gaussian. So what is happening with the Q-Gaussian at small speeds? Does it have weight on negative speeds?
The standard Maxwell-Boltzmann distributions in one dimension, they are Gaussians. In d dimension, they have a prefactor, which is x to the power d minus 1, which I guess you are referring to that one.
It should have weight only over positive speeds, no?
Sorry?
It should have weight only over positive speeds, no?
Well, the general expression is speed power d minus 1. Here, they used log linear. If instead of linear, they had used the square, it would be more clear that this is not a Maxwellian. Okay?
No, sorry.
But I don't want to, I don't know who is the you. I would prefer any more delicate point or long point, because this is not delicate, but it's long. I would like to discuss this at the end.
Okay. Yeah.
Okay?
I also have a question that I hope is not long and neither delicate, because few slides ago you told us that the parameter Q can be related to to essentially how the number of degrees of freedom scale with n, let's say. So here, do you have an analytical or let's say a theoretical way to understand these deviations in terms of?
This is what I'm going to show to you in the next 2 slides. So with Christian Beck from Queen Mary College, we published about 1 year ago the answer to your question. So here you have the analytical expression of Q as a function of the density of molecules, of hydrogen molecules, with a scale number. And this is the expression we obtained. And the 2 experimental points are this and this. And we can add that we expect when the density goes to 0, that Q goes to Boltzmann, ideal gas. And the blue line is our expression. And as you see, the blue line passes here, here, and here. Let me show to you another result, recent one, a few months ago, done with people from Dresden, from the Max Planck Institute, and Uğur Tırnaklı from Turkey. We analyzed the central limit-like distributions at the special point, which is the edge of chaos, between chaos and stable orbits of the logistic map, of the Z logistic map. If you take Z equal 2, you will have the standard logistic map. But we discussed general Z. And this is the analytical answer of Q as a function of Z. And this answer was checked numerically and in some examples analytically. And here you have the answer. So this is a Q Gaussian with the Q value as a function of Z, which at the Feigenbaum-Coulet-Resser edge of chaos satisfies a central limit theorem Q generalized. Another example, it appeared 10 days ago, again from the Max Planck Institute, by these people. He is the director of the Max Planck, of one sector of the Max Planck Institute. And they analyzed the criticality of spin glasses, which, of course, since long we know they are complex systems, is a mess with frustration and all kinds of things. And they discussed the 3-dimensional case of spin glass. And they showed that Q, as a function of temperature, goes from Q equal -1, which is the semicircle Wigner law, to Q equal 1, which is the Gaussian law. So this is another application of these kind of things. Maybe I will skip this application. Let me go to quantum phase transitions. Many years ago, with a student at that time, Filippo Caruso, he was student of the Scuola Normale Superiore di Pisa in Italy, we did this paper where you see non-additive entropy reconciles the area law in quantum system with classical thermodynamics. So, if you calculate for a one-dimensional system of some wide class, and here in particular is the Ising model in one dimension in the presence of a transverse field. And that system at zero temperature, but a finite value of the transverse field, it has a quantum phase transition, a critical one. So this is sometimes referred as quantum criticality. And we analyze what happens if the system is of this size and you are focusing with your laser or whatever this size. This goes to infinity, and this is quite large, and we analyze the entropy of that part. In fact, when we say the entropy of the table, we are analyzing the entropy of a big part of a much bigger part, which is the universe. So we always focalize not the entire system, because it would be the universe, but a part of this universe, for example, a table. So this is what we do here. And when you take q equal 1, it goes here very low, like logarithm of L. Doesn't work. We want to satisfy thermodynamics. So we change q equal 1, q equal 0.9, 0.8, etc. And then we arrive to a magic value, q equals 0.08, and we have a straight line. And there, for this value of q, SQ is extensive. That's the one we want. So I'm showing to you the computational result, but it was possible to calculate the analytical result. And here you have it, q equals this thing, where C is the central charge of quantum field theory. And for the Ising model, C equal 2. So if you put here C equal 2, Q is equal to square root of 37 minus 6, which is 0.08. Another application. This was done in France by the group of Gaël Combe and one Brazilian from Minas Gerais. And that was the validation of a scaling law that I will show you in 1 minute. The experimental validation of that with granular matter. And it was considered so interesting that is the machine. I saw it, that size. They invited me to Grenoble, so I went there. And I said, take me a photograph with the machine. So they took me a photograph with that machine. So in that experiment, they verified Q statistics, and it was considered a big issue. So there was an editor suggestion of physical regulators. And they could measure the anomalous diffusion, because while the system was moving, the grains were moving. They had a marvelous camera filming everything and processing everything. So they could verify that the distribution of velocities is Q-Gaussian as a function of the experimental parameter. And they could also measure alpha, which is the anomalous diffusion exponent, as a function of that. And they verified this. And this had been predicted 19 years earlier by a young Dutchman, Boekman, and myself, we predicted this law, and it was verified in 2015. And here you have the data, and the verification is okay within 2% of error. So it was a beautiful validation. Long-range interactions. So now let's go back to classical Hamiltonians with long-range interactions. I want you to see these lines by Gibbs in his book 1902. So Gibbs wrote, "In treating the canonical distribution, we shall always suppose the multiple integral in equation 92 to be finite. 92 is what we call today partition function. Because if the partition function diverges, the law of distribution becomes illusory. What law of distribution? His law of distribution. Gibbs is saying that if the partition function diverges, his law of distribution doesn't work. And he even says where this can happen. And this can happen in gravitation, when material points, which attract one another inversely as the squares of their distances. When you have long-range interactions, Boltzmann-Gibbs statistical mechanics does not work. And let me show to you an example of this. So here we have this with a potential attractive 1 divided distance power alpha. So if alpha is small, we are here. If alpha is large, we are there. And this can be in 1, 2, 3, 4 dimensions. And it is easy to check in 5 minutes that there is a special bisector, alpha equal d. And when you are above this, the total energy of the system is extensive and fine. But it happens that Newtonian gravitation is here. Alpha equal 1 and d equal 3. And here, the total energy is non-extensive. So in this region, Boltzmann-Gibbs statistical mechanics might work, but here, it doesn't work. Like Gibbs himself predicted in 1902. All physics professors and students should know this, but very few know it. But Gibbs knew it. And I have suspicions that Boltzmann knew it also. So I'm going to show to you an example in the dangerous region here. So I will take the XY example with long-range alpha interaction, not first neighbors, but first, second, third, fourth, fifth, decaying with distance, like 1 divided the distance power alpha. And I'm showing to you an example, alpha divided by d 0.9, which is in the dangerous region. And with these people, we did a molecular dynamical simulation just from first principles, using force equal mass time acceleration. That's all. 1 million of coupled equations, force equal mass time acceleration. And to solve this, you must use computers. And we did. And this is what it came out. Here you have the distribution of velocities. The distribution of velocities as a function of the momentum, the velocity, if you wish. And the system does not like Maxwellian. This is Maxwellian. Q equal 1. The system likes this. We checked this for D equal 1, D equal 2, D equal 3. It doesn't like it. It likes this. And this is a Q Gaussian with Q close to 1.6. Let me emphasize that in this paper, and many others, we did not use the concept of entropy, any entropy, nor the concept of temperature, nothing. Just mechanics. Force equal mass times acceleration. A lot of elements, you make averages, blah, 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 and you get the result. And the result is that the system does not like Maxwellian, which is this, likes Q Gaussians. But this is the distribution of momenta. Then we said, let us check the heart of Boltzmann-Gibbs statistical mechanics, which is the Boltzmann-Gibbs factor, exponential of minus beta times the energy. Let us check that. So we did, and here you have it. Log, linear, this is the energy. And the system does not like the Boltzmann-Gibbs factor, Q equal 1. It likes this, which is Q equal 4/3. It likes this for D equal 1, D equal 2, D equal 3. Definitively, it does not like what is written in the textbooks from first principles. Let me now go to another application, which I find marvelous, and whose main protagonist is precisely Ayrton Deppmann, who is sitting there from the University of São Paulo. So there are, I don't know, thousands of papers, experiments in high-energy collisions of elementary particles. And in this, LHC, CERN, Brookhaven, etc., they appear systematically three magic numbers, 1.14, 1.11, 1.07. Why three numbers? And let me show to you that this is the LHC. This is the detector, the Alice detector. You see the size of a person. You see this is a monster. And they invited me there, and they took me down Earth 80 meters. We took a coffee inside the Earth. And they showed to me the accelerator, etc., and we arrived to the door of the detector, which is this. And the guy told me it was like a film of James Bond. Everything was checked, the eyes, etc. Terrific. They are very, very afraid that some terrorist goes there and puts a bomb. So he asked me, that's the door of the detector. How heavy is that door? I said, I don't know, many tons. It's very heavy. Heavier than the Eiffel Tower. I said, you are kidding. Yes, this door is heavier than the Eiffel Tower, and it takes 2 days to close it. I said, wow. Can you take me a photograph? And they took me a photograph, and there it is. So, in this experiment at LHC, they have log, the probability, and here, momentum. The transverse momentum. So you have the collision, you have a big mess, and then the system ejects hadronic jets, and they analyze each of those hadronic jets, the longitudinal part and the transverse part. And I'm showing to you the transverse momentum. So you have here 1, 2, 3, 4, 5 experimental situations with different energies, different detectors, etc., etc. And you have these lines here, 1, 2, 3, 4, 5. And in this picture, there are several amazing facts. I would say that the first most amazing fact is the talent of the experimentalists that can do experiments on a single shot down to 14 decades of precision in a single shot. Bah. So it's fantastic to have experiments like this. The second most amazing fact is that all these are very well fitted by this q exponential, this simple expression here, with q equal 1.14. And this system does not like Boltzmann-Gibbs. This is q equal 1. Does not like it. Does not like it at all. At this region, Boltzmann-Gibbs statistical mechanics is millions of times wrong. Not 10% wrong, millions of times wrong. But this number is there and it stayed mysterious during many years. Why 1.14? And the mystery was, there was a second number. I showed to you 1.14, 1.11. 25 years ago, Johann Rafelsky and a student of him made these physical regulators, and for the dynamics diffusion of charm quark, they found q equal 1.11, not 1.14, 1.11. And that became a double mystery. In some experiments, 1.14. In a good theory, 1.11. Why? And this was clarified by Ayrton Deppmann, Eugenio Mejías from Spain, and Deborah Menezes from Florianopolis, who is now director at CNPq and who was the first woman to become president of the Brazilian Physical Society. So they published this paper using Young-Mills field theory and quantum chromodynamics in the one-loop approximation, and they found a beautiful little formula, which you see here. Q as a function of the number of colors and the number of flavors. And if you put 3 and 6, this gives you 8 divided by 7, which is 1.14. First mystery explained. But if the quarks that are diffusing are heavy, like the charm quark, you must use not 3,6, you must use 3,3. It is known since long. And then Q becomes 10 divided by 9, which is 1.11. Second mystery solved. But other experiments, I was showing to you experiments here, but there are experiments here. And here, they have Q equal 1.07, not 1.14, not 1.11, but 1.07. And this mystery was again solved by Ayrton Deppmann and collaborators. I had the privilege to be collaborator of that one. And they used this, and to make a meson like that of Cesar lattice, the pions. You need 2 quarks, 1 and 2. And then you have a meson. And because of these 2, it appears here a number 2. And when it appears here, number 2, Q equal Q equal 1.14, you put it here, and you get Q bar equal 1.07. Verified experimentally. The third mystery solved. So I am in love with their little formula because it is fantastic. going to the end, one more application, maybe two more applications. That one is with black holes. Stephen Hawking published in 76, a paper which is very known and very cited, which is Black Holes and Thermodynamics. And it is called the Bekenstein-Hawking entropy. They used the Boltzmann-Gibbs expression of the entropy, and they got this, that the entropy of a black hole, sorry, not the entropy, the Boltzmann-Gibbs entropy of a black hole is proportional to the area. It is like this. Very interesting result. But problematic, because this entropy is not extensive. It should have been proportional to the volume, but it's not the volume, it's the area. And therefore, it violates extensivity of the entropy, and therefore it violates the Legendre structure of thermodynamics. So it's a very interesting result, but it violates thermodynamics. So this I didn't like since many, many years. And in one occasion, I was invited at the Academy of Science of the Vatican, inside the Vatican, and this came out in the discussion, Bekenstein-Hawking, and then I made the remark, yeah, it's very interesting, but this cannot be the thermodynamical entropy. It is Boltzmann-Gibbs entropy, which is very good, but it is not the thermodynamical, because to be the thermodynamical, it should satisfy Legendre structure, and it doesn't. And as you can guess, inside the Vatican, we were hosted at the unique place where there are apartments inside the Vatican, which is where the cardinals stay when they make the conclave. And I was in one of those. And as you can guess, during the night, the Vatican is very, very boring. And so I had nothing to do. And so in my apartment, I was trying to find what is the value of Q that would make the entropy of a black hole to be extensive. And I couldn't find it. And the second night, I couldn't find it. I said, what's going on? And then suddenly, I thought, oh, I will not find it because it's not SQ. There is no value of Q that will work. It's some other entropic functional. And it happened that in my book, 2009, I had a footnote with another entropic functional that I called S delta. And I remembered it. Oh, maybe it's that one. And I put it, and it was that one. So I published a paper with a student of mine at that time. And I put the title, practically the same title as Hawking, Black Hole Thermodynamical Entropy, because he had called it Black Holes and Thermodynamics. So in that paper, what we say is Bekenstein-Hawking is an interesting result, very interesting result, which can guide things in string theory, cosmology, etc. But it is not the thermodynamical entropy. It is something different. The thermodynamical entropy needs delta equal 3/2, and not delta equal 1, which is Bekenstein-Hawking. So we published this. Some friends were telling us, you're crazy. You are saying that Hawking is wrong. Well, yeah, I'm saying that Hawking is wrong. Not in the expression. The expression is beautiful and extremely interesting. It's the ratio of the area of the black hole divided by the square of the Planck length. So it's extremely interesting. But it's not the thermodynamical entropy. We said that. And Well, here you have the SQ that I mentioned to you. Here you have S delta, so you see it appears here. Doesn't matter this, but it remained in the community this value of delta equal 3/2, and not delta equal 1/2, 1. And then was done ice cube neutrino observatory results with neutrinos, and this is the observatory. And when I see this, I say, well, these experimentalists must love very much nature, and more specifically cold nature, because it is in the center of the South Pole. And this is where they make the experiments, and they found, as analyzed by Peter Gisba, Giuseppe Lambiasi, delta equal 1.565, very close to 3/2. So I was very happy, that's great. And this definitively excludes delta equal 1, which is Bekenstein-Hawking. And then came data from the Planck Observatory. Yeah, that's a very important question. It happens that surely Nathan and other people can explain to you this better than I. Many people think that what is valid for a black hole is valid for the universe. So in that holographic scenario, that holographic model of the universe, of a cosmological model, we are inside a black hole, which is the universe. And they do that all the time, and they publish thousands of papers with that result. And it is relevant and probably correct in many issues. This is the connection.
Sorry, but the title of the paper is Tsallis cosmology and its application in dark matter physics with focus on ice cube, high energy neutrino data.
Yeah.
So what is this paper? How is this paper related with black holes?
But I'm telling you, they are using these people.
So you're saying they are doing holography?
Sorry? Yeah.
They are doing holography?
Yeah, yeah. They are using a holographic model of the universe. There are thousands of papers that do that. I don't remember very well. It's a long time I read this paper. I don't remember. But the important point was the crossing of this curve with 1. And that crossing occurs for delta equal 1.565. But you have the reference there. You can check details. Then arrived data from the Planck Observatory, not from the South Pole, but from the air outside the Earth. And it was this paper by these people and from Iran. And I hope none of the bombs that Trump is sending to Iran would kill any of them or their families. And they published the analysis of the Planck Observatory, and they had these two tables, two different approaches, and in that approach, they obtained delta equal 1.87. And the other approach, they obtained 1.26. So there are two different approaches, and they get these two numbers. It came to my mind, could it be that their two approaches are an upper bound and a lower bound of the correct answer that they were incapable to calculate? So I took the mean value of 1.87 and 1.26, the mean value. And guess what? It is 1.565. I said, amazing. The mean value of the data of the Planck Observatory coincide with all the digits with these that come from the South Pole. So that was for me a miracle. And I wrote to the authors of all of them, are you aware that the mean value, blah, blah, blah? So I had a correspondence about that. But let me go on. Then appeared another paper in which, from a different type of measurements, not neutrinos, but the abundance, the relic abundance in cold dark matter, and they found delta equal 1.499. I said, wow, incredible. And then came another paper by these people from Poland, and they found that delta is above 1.43 with a variety of data in cosmology, observational data, which of course is not 1.5, but which once again excludes Bekenstein-Hawking. Then came another paper again. This was a few weeks ago by people from China. They used all these cosmological observations and they calculated delta, and it is around 1.28, not 1, not 1.5. So I was very intrigued by this. What about that? This is not 1.5, it is not 1. In any case, Bekenstein-Hawking entropy is out of the game. But then, for a variety of reasons, I studied this situation, and it's in the press, a Europhysics letters that will appear maybe in 10 days, 15 days, in which I suggest that either for SQ or for S delta, the value of Q microcanonical is not the same as the value of Q canonical. It is smaller. And that the delta microcanonical is not the same as the delta canonical. By taking this into account, it comes out these two pictures. This refers to SQ. This refers to S delta. So here, you have the figure that I showed to you before. This is analytical, and this is analytical. And they are different. So this corresponds to the canonical distribution, and this corresponds to the microcanonical distribution, because I obtained this by imposing equal probabilities, which is the microcanonical hypothesis. And they are different. They only coincide when they are equal to 1, which is in the textbooks that you have studied. You have studied that in the thermodynamical limit, the microcanonical ensemble and the canonical ensemble coincide. Fine, but not out of Q equal 1. Out of Q equal 1, they are different. And the canonical is between the microcanonical and Boltzmann. Is in between. The same for S delta. Here you have Boltzmann, delta equal 1, Bekenstein-Hawking entropy. This is the expression that I obtained for the microcanonical ensemble, is this simple analytical expression that you see here, there, and D equal 3 means 3/2. There you have the value for D equal 1/3, this is 3/2. Okay. So this is the D-dimensional expression of the 3/2 business. And this is the asymptote, which you calculate in 3 minutes. And here you have the value of the asymptote. And here are the data that were very close to 1.5, and here are the data that were very close to 1.28. So what I suspect strongly is that the observations of these data are somehow using an isolated system. And the observations that obtain this are somehow interpreted with a system somehow in contact with some funny thermostat, and don't ask me what is that thermostat. And also I verify that the canonical tends to saturate here, and therefore this is the asymptotic behavior, and therefore the canonical expression, which nobody has calculated, would tend to saturate, and if it tends to saturate, it becomes even better. So this is the present situation of this. And Bekenstein-Hawking is out of the game. Not as Boltzmann-Gibbs entropy. It is precisely Boltzmann-Gibbs entropy. It is out of the game for thermodynamics. So if you want to calculate a susceptibility, something, a specific heat of a black hole, I don't know how one would measure the specific heat of a black hole, but better you don't go very close to it. If you want to do that, you need to satisfy thermodynamics, and therefore you cannot use Bekenstein-Hawking, and you can use S delta. So as my last application, I would like to tell you an application to sciences of health, and there are many such applications of Q statistics or non-additive entropies to medicine, etc. And what they do here, they introduce in the brain a deep brain microelectrode surgery. So they put a little bit of anesthesia here, and they put a needle that goes near the hypothalamus. Of course, they don't do that for any neighbor in the surroundings. They do it for very severe Parkinsonian people and epileptic people. So they go there and they install a little chip there. And they get out the needle and they go home. And when the crisis arrives, the little business that they left there makes and it aborts the crisis. So the guy with Parkinson has no more severe Parkinsonian symptoms. This is what they do. So, by coincidence, I happened to get knowledge of these people from Belém do Pará. This is the leader of the group. Those are students. And we are right now submitting for publication what I'm going to show to you. Here you have, while the needle is going inside, it measures the electronic microvolts that are in the neighborhood of the needle. And here you have two examples. Outside the subthalamic nucleus and inside the subthalamic nucleus. You have here and here. I first saw this. And when I saw this, I said, wow, this is not Brownian motion. This is not Brownian motion. This is not Gaussian, because it has spikes, chick, 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 and other characteristics. So when I saw it, I said, this could well be a q-Gaussian, not a Gaussian, a q-Gaussian. And we asked the data from the people in Belém do Pará. They sent it to us, to Rio de Janeiro. We analyzed, and they were beautiful q-Gaussians. And here you have 4 such examples. This is a q Gaussian. If q goes to 1, this goes to exponential of minus x squared, which is a Gaussian. In this representation, a straight line is an exact q Gaussian. And this is the signals coming from the brain of that person. Almost a straight line, almost a straight line, almost a straight line, almost a straight line. Of course, you might say, oh, come on, here, it's not a straight line. But this is a human being, and they are doing the experiment there. It's not CERN, where they have 14 decades of precision. Here it's medicine. So these are very good representations of these results, and the people from Belém do Pará were very surprised. Wow, these are good fittings. And then we took almost 200 such fittings of 49 different patients. And they were all roughly quite good q Gaussians, which give you q and beta. And here you have in q and beta 1, 2, 3, 4, almost 200 points. And these 200 points are like a cloud. They are like a monotonic function. And when you have a monotonic function in such a representation, that means that for every value of q, you have only one temperature. It's like when you put water to boil. You choose the temperature of the water, you choose. But you don't choose the temperature at which the water will boil. That is chosen by the system. So when for each value of q you have only one temperature, this is typical of criticality. So our brains are in criticality, which means high susceptibility, from the Latin, suscipere. And high susceptibility means that small variations of the causes imply large variations of the effects. So our brains are like this. And when I saw this, I said, I understand why the guy who is waiting the service of tennis, he's like this. Because he's an alert state. A small modification of the angle or of the velocity, he has to quickly react and do something. And the same happens with the goalkeeper in the penalty. When the penalty is to arrive, the goalkeeper is like this. He is alert. He is at criticality. He is with high susceptibility. And then I said, yeah, that's reasonable. Why you follow this red light? Why you follow it? Because it shouldn't be there. And you are alert, and you say, wow, what's doing this? And you pay attention. Why? Because we are the children of those that were close to criticality. Those who were far away from criticality were eaten by the tigers. So we inherited brains that always are near criticality. And that was my last explanation. Let me refer some details to what Ayrton said. So in May next year, it will happen in Sweden, in Lund, the Nobel Symposium in Physics. And there is every year one Nobel Symposium in Physics, one in Chemistry, one in Medicine, Literature, Peace, and Economics. The subject of the next one in Physics is Beyond Boltzmann complexity, memory, and non-additive entropy, which is that you just heard. So what I'm going to say in the Nobel Symposium next year is going to be similar to what I told you today. Thank you very much.
Thank you very much for this very comprehensive talk. We have time for questions. We have already two there. He raised the hand a few seconds before you.
I know it's very in the start of the lecture, but you had like that table after you discussed the difference between additivity and extensivity. You had a table
Yes.
showing what systems and what entropy to use.
Yes,
And I did not quite got what was the
issue.
Yeah, the y-axis of that table, x or y, the vertical one, the vertical axis.
You refer to that one.
Yeah.
Okay.
What exactly is the vertical axis?
Here you have entropies, entropic functionals, 1, 2, 3, 4, etc. And here you have systems. Systems of this class, or of this class, or of this class, or of this class, systems. So entropic functionals applied to systems give you entropies. And when you apply Boltzmann-Gibbs entropic functional, which is additive, to this family, it is thermodynamically extensive. And this is the textbooks that you have studied. But when you have this family, Boltzmann-Gibbs is not extensive. It is additive, because the entropic functional is always additive. But for such systems, it is not extensive. But this Q is extensive. And the others are non-extensive. If you have this family, and this is the case of black holes, this is non-extensive, this is non-extensive, but that one is extensive. So you change the entropic functional, and you take the appropriate value of delta, and you get an extensive entropy. And now you can do thermodynamics. So you understood now?
Yeah, I already had understood that, just didn't understood what those expressions on the left means, what
Here.
that, yeah.
These are the number of possibilities for n elements if n is large. So it is, in the sense of mathematics, it is the asymptotic behavior. So if you had n coins, these would be 2 power n. It's clear?
Yeah, it's clear. It's crystal clear now.
Thank you.
Thanks. And, okay. Thanks.
Maybe can I add, because it's very related, can I add a small... I'm a bit confused by the quantum phase transition thing, because in the quantum phase transition thing, let's say the dimension of the Hilbert space is, in any case, scaling exponentially. But you don't need to, you showed that you don't have to use SBG. So I'm a little bit confused how you compute from first principle, in which case you are, because in that case, you will guess that you have a Hilbert space that is exponential.
The calculation is simple for the microcanonical ensemble, where you use equal probabilities. It is simple in the examples that I presented to you, which are here, these, and these. It is simple in the calculation of Bekenstein-Hawking. It is simple. It is not simple for the canonical. It's a mess for the canonical. So when I say the increase here, I am referring to a very specific hypothesis of equal probability, which is not necessarily true, but which gives you the flavor of what's going on.
I see.
So thanks for the talk. And my question is about the black hole thermodynamics part. So you said that Hawking expression does not work on a thermodynamic view. So it's a common result that specific heat from Hawking entropy is negative, which would indicate that the system is unstable. So if you do thermodynamics with the S delta, does it still is unstable, or you reach some different results?
You are touching two different issues. The possible negativity of an entropy definitively indicates that you should not use classical arguments. You should use quantum arguments. That's an issue, an interesting issue. But I was referring to the other issue. Is that entropy extensive, yes or no? And Bekenstein-Hawking is not extensive if we think of a black hole as a three-dimensional object. If we think of it as a two-dimensional surface, it is extensive. But people, astrophysicists and cosmologists, they tend to speak of a three-dimensional system. And if the entropy is proportional to the area, it violates thermodynamics. So as I said, it's a very interesting expression which inspires a lot of things in cosmology and string theory, Maldacena, etc. But it's wrong if you say that that entropy is the thermodynamical one. It's an interesting one, but it is not the correct one to use in thermodynamics, in contrast with the title of Hawking, which was black holes and thermodynamics.
So if you use that entropy, you reach the same results that Hawking arrived using QFT, for example?
Not necessarily, not necessarily. Some of them are scaled differently. The scales might change. Yes.
Okay. May I ask another question? So you showed a lot of different values for Q, like some of them are small, like 1.07, and there are others that are big. So what does this value represent? It means that the correlations are long range?
Yeah, exactly.
In some sense?
Exactly, exactly. Yes, I didn't have time to develop that point, but this is a crucial point of the whole theory. I tend to call simple system a system whose time and space correlations decay with distance sufficiently quickly so that all momenta are finite. The second, the third, the fourth, the fifth, all momenta are finite. Then I say this system is simple. This is what happens if a system decays its correlation exponentially. So Boltzmann-Gibbs is magnificent for that. But when the correlations decay slowly, for example, like a power law, you cannot have all momenta finite. Maybe you have first and second moment, but the third, the fourth, the fifth, and from that point on, all the other moments are going to diverge. And if it diverges, you have the kind of difficulty that Gibbs himself said, if the partition function diverges, forget it. Forget my law. So when the decay is a power law of the correlations, the higher momenta diverge, all of them. And therefore you cannot use, you can, but you should not use Boltzmann-Gibbs statistical mechanics. In a problem for the atom hydrogen, you can use Newtonian mechanics, but you shouldn't, because it's not Newtonian. So people that sometimes use Boltzmann-Gibbs statistical mechanics for systems that are pathological, they say, no, but I did calculate everything. Okay, you calculated, but nature does not like your calculations. So you are a mathematician. You are not a theoretical physicist, because a theoretical physicist is not one supposed to do any kind of mathematical idea that comes to his mind. He should do mathematical ideas that nature likes.
Thanks.
So about this black hole thing again, if you have a bath of photons, say, which presumably
Bath of photons.
yes, presumably are described by Boltzmann-Gibbs statistics, and you have it interact with a black hole, and you want to know the thermodynamics of this whole system, how should one write down the entropy of such a thing? Because presumably the non-extensive black hole entropy can't simply be added to the extensive photon entropy. So how does one define in this framework the entropy of such an interacting system?
Yeah. You are putting a question that, let me simplify it a lot, because that's an interesting question, but let me simplify it a lot. What is the dimension of this? Well, it doesn't know. Of a sheet of paper. The dimension, well, roughly D equal 2. What is the dimension of this? D equal 3. Now, if I have this and a sheet of paper, what is the dimension of this? That's not a good question, because the dimension of this still remains 2.
So you're saying it's not a defined quantity?
Let me finish.
Okay.
And the dimension of this still is 3. So these two objects together do not have a dimension. They have different dimensions, but they might have, if in thermal equilibrium, the same temperature, not the dimension. So you will have a two-dimensional object in contact with a three-dimensional object that might be in thermal equilibrium, and from the zeroth law of thermodynamics, they will have the same temperature. What I said about dimensions, it is the same, I think, for the entropic indices. So if the photons are, say, Q equal 1, and the black hole is something different, it doesn't make sense. What is the entropy of the two together? Each of them has its entropy, like each of them has its dimension. But if they are in contact, there might happen thermodynamical things. And those thermodynamical things, you must calculate them with a thermodynamical entropy for this and a thermodynamical entropy of that. Otherwise, you are going to have a salad.
All right, thank you.
So thank you for the talk. I have a more practical question. Like, imagine that someone comes up for you with a statistical mechanical systems. What would be like the key signatures that you will look for?
What would be the
What would be the key signatures that we will look for to see if we are beyond Boltzmann-Gibbs entropy, right?
If it is a Hamiltonian system, because it could be a dissipative system, but if it is a Hamiltonian system, the answer is very simple. The two key is the distribution of velocities. Is it a Gaussian? And the distribution of energies. Is it an energy? Is it an exponential? If it's not, you're certainly out of Boltzmann-Gibbs. If it is dissipative, it's more delicate, because you can have, you will have dumping. If you have over-dumping, you can neglect the inertial term, and it leads you to q-entropies if you have over-dumping. So it's not conservative, not over-dumped. In between, what is it? This we don't know.
Okay, Nita?
So I had the question about the particle part that I guess Ayrton also worked on. The question was, you had a formula which just depended on the number of colors but doesn't depend on the coupling constant. So if you do free Yang-Mills, you would also get Q being non...
You mean this formula?
Yes.
Yeah. What do you want to know, maybe?
Yeah, in fact, in this work we got the running coupling for the QCD in a non-perturbative approach. And the running coupling follows a Q exponential, and the value of Q is calculated in this way. So Q depends on the quantum field parameters. And you have, for QCD, the number of colors and the number of flavors. We are developing another work where we calculate for QED. And for QED, it's a different formula.
Sorry, I just don't understand. There's no coupling constant in formula.
No.
So
no, in this work, we get the running coupling is one of the results of the...
oh, sorry. Suppose I do the theory with zero coupling. It's just a free, you just have free gluons and free...
No. Zero, no.
No,
Different from zero and small, yes,
no, the
but
formula,
not zero.
The formula doesn't depend on the coupling constant.
If it is non-zero.
No. Okay, I don't understand.
Yeah, well, if you have just quarks and you don't have gluons, then of course you have probably something that will not interact, and so I don't know. This is for Young-Mills field theory, and you always suppose that you have two fields that are interacting. So if you don't have a Young-Mills field theory, maybe this is not valid. So, but I cannot imagine something in physics.
Okay, we can talk later.
Yeah. Okay.
Some more?
If you modify the entropy of the black hole,
Yes.
you also modify the mass because you need to satisfy the first law of thermodynamics, right?
No, I don't modify the entropy. I say Bekenstein-Hopking is the Boltzmann-Gibbs entropy. And it depends on the mass, on the charge, on the angular momentum. All these, I touched nothing there. I only say don't use that to make calculations in thermodynamics.
Yeah, this is my question. So the first law of thermodynamics
Yes.
say that the delta M is equal to T delta S, right? Where S is the thermodynamical entropy.
Yeah.
So if you use your thermodynamical entropy in the first law of thermodynamics, you need to modify what is the mass, right? To satisfy the first law of thermodynamics. Do you agree?
I'm not sure if I understand all
My question is
what
that
you said.
your entropy satisfies the first law of thermodynamics.
Yes.
So then you need to modify the mass, right?
This,
Because the
I maintain in
Bekenstein-Hopking
suspense. I don't know.
the Bekenstein-Hopking entropy satisfies the first law of thermodynamics when the energy is the energy of the black hole. So if you modify the right-hand side of the first law of thermodynamics, as you do, you need to also modify the left-hand side, right, to have an equality. You cannot modify only one side, right?
Right. Yeah. But people from the beginning, Bekenstein, I think he was the first, he used analogies between mechanics, between gravitational mechanics and thermodynamics. And he said, look, this behaves like this like this. And then he arrived to the Bekenstein, which quickly became Bekenstein-Hopking entropy. And all this is perfect. But what they were referring to as thermodynamics was an analogy. It's not a thermodynamical entropy. So to analyze the implications of your question, we should have to discuss more, and perhaps you should have to discuss with people from cosmology and not with me. What I can tell you is that the entropy S delta satisfies thermodynamics and satisfies the zeroth principle, first principle, second principle. All this is okay. For Bekenstein-Hopking, it is not okay, because maybe I can write something here. If F, the Helmholtz energy, is U minus Ts, if this is scaleless, no scale for T, and this goes like L square, if this goes like L cube, it doesn't work. This is the problem of Bekenstein-Hawking.
So you
what
think
is
that the temperature doesn't have scales?
Sorry?
Do you think that the temperature doesn't have a scale?
Yeah. If you make this hypothesis, which is normal,
Okay, so you say it's intensive, and the other are extensive.
yeah. Because if this goes like L cube, this goes like L square, you have a problem here. The Legendre structure of thermodynamics says that this, and this should scale like L power D. Not half of it power cube, and the other half power square. It's not like that. You violate thermodynamics if the entropy is not extensive. This is what the Bekenstein-Hawking entropy does.
Thank you.
Okay, so I think it's time to thank Costantino again.
Thank you.
Hilda Cerdeira. She sends her regards, but she yesterday did a vaccine. You need to remove from there as well. From there. So she did the vaccine yesterday and she didn't feel well. Sorry, so she couldn't participate.